Well,
I think it's going now.
all right. So
You're missing the word in the second line.
turning genes off, yeah. Okay, without DNA methylation, and this is where you finally, we're getting to this very last picture. And I have a story about that. So this happens probably a lot in our DNA. And we're going to end up talking about this in its relationship with cancer. Okay, this is going to represent a CPG island. Okay, and we're going to have some chromatin. Okay, following it. And sometime during embryogenesis, some transcription factors were bound to the CPG islands to activate transcription. Okay, but eventually they leave. Okay, so at some point as the cells begin to differentiate, the concentration of that transcription factor is probably going to diminish. And they leave. Okay? This allows another complex of proteins to bind, and this complex is, I'm going to have to make it red. PRC2. Okay, this is the polycomb repressive complex 2. There's a PRC1, it has a different role. Polycomb. This was named after a certain phenotype in fruit flies. And it had to do with the segmentation, so I'm not sure they had like regular heads, thoraxes, and abdomens. They had something else. Okay, you only find PCR2 wherever there's a CPG island. Okay, nobody knows why. So how that PRC2 lands specifically on a CPG island, no one quite knows the story yet. It might have to do with some long non-coding RNA. So we might be revisiting this story a little bit. There are several components to a polycomb repressive complex. Okay, but there's one in particular. The key protein within the polycomb repressive complex is the protein EZH2. And EZH2's job is to phosphorylate K27, or methylate K27. Okay, so HMG is a histone, EZH2 is a histone methyltransferase 4 H3 K27. Okay, other proteins, there are other proteins in the complex. One just enhances the activity of EZH2. Other proteins, one seems to be binding to DNA, but it's not selecting CPG island, it's just binding to DNA, and then there's some other scaffolding proteins that hold the complex together. okay? Eventually, a protein is going to land on H3K27. And I think I've introduced the protein once already. And that protein is PC. Okay, and it tends to be found in PRC1 has the PC protein. Okay, now the thing about the PC protein that makes it critical in this particular case is this leads to chromatin compaction, just like HP1. So once you get a whole bunch of histone H3K27 methylations, we're going to make them red. PC binds okay, and it does the same thing as HP1. It compacts the DNA. So these guys are interacting with each other. I think you could call them chromoshadow domains, because that kind of falls under the category that these guys have a chromoshadow domain that selects H3K27 methylation. So here's all the PCs. Okay, now this does not normally attract DNMT3. So under normal circumstances, if these are the CPG sequences, these would stay unmethylated. So remember, HP1 can bind to DNMT3. In fact, that's an important function of the HP1. But PC doesn't bind to DNMT3, okay, normally. I don't even know if there's ever a situation where DNMT3 binds to PC. So that's how these guys, even though the chromatin's compacted and it looks a whole lot like heterochromatin, the DNA remains largely unmethylated so that it could be turned on. So some more recent studies are looking at the fact that when there's an imbalance in the cell of EZH2 or DNMT3, there is a binding site on EZH2 that allows DNMT3 to bind. Now this is not normal. This, under the normal concentrations of EZH2 and DNMT3, that is not a typical reaction. However, if you get overexpression of DNMT3, or if you get overexpression of EZH2, okay? So this forms when there is too much DNMT3 in the cell or EZH2, and I've seen lots of papers now that are showing a strong relationship between EZH2 overexpression and cancer. I think under stressful situations, like overexpression of EZH2, that EZH2 can also be a docking site for histone deacetylases. Okay, so that would predict the fact that if you get overexpression of EZH2, or if you get some abnormal expression of DNMT3, that would predict that genes that are silenced this way are more subject to being silenced by DNA methylation. Does that make sense? It turns out that that's true, okay? So genes silenced by the PRC2 are more likely to be DNA methylated. Okay, by DNA methylation. In cancer. Okay. So this is a little bit against the notion of the original people who were looking at, oh, we can silence tumor suppressor genes by DNA methylation. Because back when the prostate cancer paper was published, people thought it's a random event. Any gene in the genome could be silenced by DNA methylation. And then just a whole bunch of statistics suggested, no, it's not a random event, because you see a disproportionate number of tumor suppressor genes being silenced. Okay, so this piece of data supports the notion that no, there are some genes that are predisposed to being silenced by DNA methylation. And that's more the current idea now, is that tumor suppressor genes are somewhat targeted because of how they're regulated. Okay, don't think I left anything out. Oh, there is a tail end. There is a tail end to this story, and then we're done. Okay, any questions about this part? Okay. So for those genes that have been identified as having been controlled by the polycomb repressive complex, it turns out once the DNA has been methylated, I'm going to draw a couple. The DNA is silenced by the DNA methylations. And consequently, and this is not in the handout, K27, okay. You lose the signature, you lose the methylations on H3K27. So once we transition from a gene controlled by the polycomb repressive complex to a gene silenced by DNA methylation, you don't need these histone modifications anymore. So this is what you see in cancer. You see this transition from a gene filled with H3K27 methylations to a gene that's now DNA methylated, but no longer methylated as H3K27. And and lots of genes have followed this progression in cancer. Okay, so almost done here. So I do want to look at a little bit of, we're gonna look at this on, in review on Wednesday, but I want to kind of set the stage of one way of thinking about we're going to look at a situation of a gene that happens to be considered poised. This is a gene that this is RNA polymerase. It's right at the beginning of the stage. This is a stalled RNA polymerase. So a poised transcription is transcription that's been initiated. The RNA polymerase has stalled where it usually stalls, about 40 bases into the transcript, and it's just sitting there and not progressing forward. The only phosphorylations are on 5, okay, serine 5. Okay, interestingly, these guys, if you look at their the kinds of histone modifications they have both activating and inactivating. I should have just put balls on here. They have both signatures, an activating methylation on H3K4 and an inhibiting methylation on H3K27. And all it takes is something to bump the RNA polymerase off that stall, or to simply release the RNA polymerase. So this kind of a situation is easy to turn off the transcription, okay, by bumping off, you can demethylate the H3K4s, or promote transcription by knocking off the H3K27 methylations. So a lot of genes are sitting here in this, it could be active, maybe not active, yeah, it could be, I just need the right signal. Okay, the signal appears to come from phosphorylating S2, okay? And that makes sense, because then that's going to bump So in order to bump the RNA polymerase off the stall, you need to phosphorylate S2. Okay, not necessarily take off the S5s. I'm going to put the 5s on. Do you remember the enzyme that adds the serines to S2, or the phosphates to serine 2?
Is that PT?
You can't be close enough. You get it.
Yeah.
You got it. PTEFB. Okay, something's got to attract PTEFB to the scene here. It just doesn't wander by and say, oh, I'm going to phosphorylate the C-terminal domain and put a bunch of ATPs on serine 5. It turns out, and there's probably tons of transcription factors that do that, but the one I wanted to point out is, I know, MYC. MYC's activation domain is a binding site for, oops, it's a PTP. So MYC can bump its transcripts, or its RNA polymerases that it controls. It can bump it off their stall and move genes forward so that genes for cell division are transcribed. And probably others. It's just that everything I look at when I'm looking for an example of, oh, well, who recruits PTEFB? MYC happens to fall under every category. So when we move into RNA interference, MYC is a big player in RNA interference. So MYC has been a part of every single story. You can just arrange some more little genetics around MYC. Okay, that's all as far as I want to go today. Monday we're going to work, so we're sort of done at this point with histone modifications. We'll do DNA methylation a little bit on Monday, talking about imprinting. And then on Wednesday, I want to help, let's do some things in class that help pull all this information together. Okay. Bring your questions also on Wednesday. I don't want to leave any holes. You can hit the